Hi, we are Team SensNC. My name is McKenna Downey.
I'm Joshua Wilson.
And this is our creativity pitch. In order to measure the free fraction of valproic acid, we diluted the serum sample to a predetermined amount in order to unbind the valproic acid and albumin. The diluted sample will then only contain free valproic acid. The sample will be split and sent to the impedance sensor where the total amount of VPA bound to BSA will be determined. The other part of the sample will be sent to an Amperometric sensor where the amount of total VPA will be determined through a series of enzyme reactions taking place on an electrode.
The current we produce will be directly proportional to the concentration of total valproic acid from the relationship described in the Cottrell equation. We will find the bound serum albumin from the impedance of our serum by sweeping a voltage with varying frequencies across the serum. Finally, we can use both of these measurements to back calculate free VPA.
Our sensor works by using multiple enzyme reactions to measure the total valproic acid concentration in the serum sample. The VPA solution in the serum will be placed in the sensor and travels through the outer membrane to undergo the first enzyme reaction in the acyl coenzyme A synthase layer, or E1. The product of the first enzyme reaction is acyl CoA, or P1, which becomes the substrate for E2. After traveling through a semi-permeable membrane, P1 undergoes a second enzyme reaction, E2. The product of E2, hydrogen peroxide, travels to an impedance electrode where the electrons in the solution are used to measure the current. This is used in the total VPA concentrations using the Cottrell equation. The total predicted time for our sensor to produce a reading from the time the sample is taken is about 3 minutes. Once the sample is taken, the serum goes to the first reaction chamber, E1, to produce acyl CoA, where it runs to completion. An extra 30 seconds is allotted to ensure the reaction comes to a completion no matter the initial concentration of VPA. Next, the product will move to the second reaction chamber where the acyl CoA is oxidized into hydrogen peroxide. This reaction utilizes a 20-second stabilization period to reach 10% consumption. Lastly, the signal processing is utilized to find the amount of VPA from the current and an output is generated.
The user will be able to interact with the device from thumb wheel and buttons and will find any outputs from their sample on the screen. We will also use LED indicators to communicate the stages of operation. Another way the user can receive information is from Bluetooth pairing. The front end of both of our sensors' transduction is the 805941. It controls the voltage biases and converts input current into a readable message that we can receive on our microcontroller. Low voltage and current on the board reduces the risk of injury if a malfunction is to occur. It is a compact system which translates to the portability and easy storage. With the testing of the impedance sensor, we used various combinations of resistors and capacitors to simulate the numerous impedance loads. Many of the results created were consistent with expected results. We were able to make clean graphs with low capacitance and high resistance loads. We applied 5 millivolts across the load while adjusting the frequency between 10 kilohertz and 20 kilohertz. During the current sensor testing, we used various analog devices and saltwater testing and replacement of the serum. We were able to produce an exponentially decreasing current versus time graph, which was an important aspect so we can use the Cottrell equation. Our sensor was able to transduce a current of 100 to 350 nanoamps with an applied bias of 0.1 volts. Our low power potentiostat circuit can expect a typical current of 80 picoamps, which is much lower than our expected current measurements.
Again, we are Team SensNC, and this is our creativity pitch for our Vase biosensor.
Thank you for listening to our presentation. We hoped you enjoyed it.
Good afternoon. My name is Marco Blom, and I've been asked to chair the Q&A after this pitch. And I know there are several also jury members, creativity jury members in the call, so I'd like to ask if any one of them can kick off by asking some questions, and it would be nice, of course, if team members of the team here can answer them. So anyone would like to kick off?
Yes, this is Philippe Renaud. Can you hear me?
Yes.
Oh, okay. Okay. So thank you for the really great presentation. It was really good and interesting. I have a very technical question. You you always talk about impedance sensing, but at the end you do mostly amperometric sensing. So what's this? What is really? I didn't get the point of measuring at higher frequencies and measuring capacitance, whatever. Where at the end you measure just the production of peroxide and a DC current.
Yeah, so our sensor actually took both measurements. So we used the impedance and the current for the amperometric and impedance sensors because we needed to measure two separate concentrations. So the amperometric sensor at the end there showed the concentration of total valproic acid in the serum, while the impedance sensor was to measure the bound serum albumin. So the impedance sensor that you saw on the third to last slide, I believe,
yeah.
We were using analog devices. So we were using capacitance, our capacitors and resistors in series and parallel and such to get these measurements that we were testing because we were unable to use the serum in the lab. And then those were some graphs outputted from our capacitor, so we could show that there's a decreasing frequency and impedance measurement, which is what we were expecting. And then at the, I believe, what was your second part of your question? I'm sorry.
No, I think you basically answered. So you have really two measurements in parallel. One is impedance for measuring the total albumin, and the other, which is a true amperometric sensor for just measuring the peroxide that is produced.
That's absolutely correct.
On the impedance sensing, you do that because you want to have the level of albumin, but many other parameters can influence the conductivity of or the impedance of the solution.
Right.
How much are you certain to measure the albumin concentration and not something else?
So we're in our sensor, we actually divide two separate processes. So one separate portion of the sensor is only the impedance sensor, and then the other portion is the current. So they're actually separated from the two.
Yeah. Okay.
So maybe I see there are some other questions actually in the. So is this sufficiently answered?
For me, it's okay. Thank you. Yeah.
Okay, perfect.
Thank you.
Then I see that Tony Cass was the first one to raise a hand.
Okay, thank you. Very nice talk. Very clear what you were aiming to achieve and how you got there. But I had a question about specificity. So your enzyme reactions, as I understand, are not specific for valproate, but would happen with any carboxylic acid, including endogenous carboxylic acids. And so I was just wondering if you had some thoughts about how you'd avoid that problem of non-specificity from endogenous molecules in your sample.
So you are correct that our enzymes are not specific towards just valproate. So I guess our approach would be to kind of just know what we're looking for and know what the output results should be. So if we're getting different output results that we shouldn't be getting, we'll know that our enzymes are not reacting with what we expect them to be reacting with. So I guess it's more of like since we couldn't test in the lab, it's more of like an expected result through calculations that if we're getting like an abnormally large concentration or an abnormally low concentration, we know that our enzymes might not be reacting with the appropriate target molecule. So I guess it's more of a kind of looking on the output and then going back and saying, okay, what can we do to see if we can get the right measurements?
Okay, all right, thank you.
Okay, thanks. Moving on, Lou Segering also had a question, I see.
Yes, thank you. Thanks for this presentation. I'm just wondering, that it's quite early where you are at the moment, but it doesn't matter. So you're diluting the serum as a first step, and then you assume certain conversion reactions for the enzyme reactions. What do you think it will cause? What kind of error will it cause for the final measurement you do? So if I have to dilute, or is it something in your system that is already diluting everything? How How do you guarantee that everyone is doing the right stuff? So do you have controls involved that everything is working more or less?
Yeah, so we're diluting at first to unbind all of the valproic acid in our sample, so that we can then go through and have those enzyme reactions, and that they'll react how we expect them to. And then we're using the two sensors, the Amperometric and the impedance sensor, at the same time to measure both the total and then back calculate the bound valproic acid. So we'll first get the total amount of valproic acid, and then the impedance sensor will then go through and calculate the bound so that we can go back and figure out how much was bound at first.
Yeah, that's true. But if you do not, so you will make, I assume that you will make errors when you dilute the stuff. How will that influence the result? So because you have a certain amount of valproic, or is it always the same? And then you look at the ratio between the two, the unbound and the bound one.
Yeah, so we didn't get to test the dilution experiment as much because of the pandemic, but we are expecting to be able to find a dilution constant so that we are able to dilute it the same amount each time, and then we'd be expected to get the same bound versus unbound concentration each time.
So you have to dilute it yourself. It's not in your system that it is automatically diluted there.
Yes,
I heard someone else, isn't it?
We definitely talked about kind of that being an error in the system and had come up with a few different ideas for maybe how someone would kind of do that themselves, just because that really can't be expected by just the average person. And so we had talked about maybe including like vials or like different kind of pre-measured amounts as part of the kit that could be like a consumable to make it easier to interact with.
Okay, yeah, that sounds as a good idea, because I don't think people can do it themselves, at least I cannot do it at home.
Right, exactly.
Thanks for the answers.
Okay, thanks. Indeed, as I forgot to comment, it was a very nice presentation, indeed, clearly highlighting your approach with indeed some attention points as the questions pointed out. So we have 3 minutes left. We can have one quick question, maybe, if someone comes up with a quick, well, maybe easily answerable question, ideally even then. If not, then I can build maybe a little bit. It touches a little bit on what we discussed, or specificity. So do you think you can get away without any sample preparation? So basically, will your sensor in an optimized form be good enough to do that, you think?
From the calculations and kind of the testing that we used online and other analog devices and things as well, our current sensor can most definitely be able to transduce the signal that'll be produced possibly in the lab. But of course, no biosensor is perfect without lab testing. So if we're trying to translate this into the public environment right after testing at home, most definitely not. We would definitely need to do some lab testing.
Yeah, no, I mean more in general use. So if you have a sensor, if it will need to employ all the time a formal sample preparation to be included before you actually start your sensing protocol. I mean that's you only know when you test. But I was wondering about if you have any expectation on that, if you can start straight away or expect still to need some steps. It touches a little bit on the other questions.
Are you like referring to like our dilution step before we put the sample in?
It's in a sense part of the sample preparation, yes. So in that sense, it was partially already answered, and I think we're running out of time also. But I think it's so in that sense the question was partially answered. I think the rest indeed, we need to prove itself in a lab testing environment. So I think we need to conclude this session. Thank you very much.
Thank you
for the nice work. And then we go back to the organization, I guess. The next speech.
Thank you so much.
Thank you.
Hi everyone. So today we're gonna look at the working principle of the cytochrome-based biosensor, which is designed by Sense Glasgow team. So this biosensor has 4 main chambers, and it's based on a 2-step assay. So first, valproate molecules will be captured and isolated from the plasma sample using selective antibodies immobilized on microbead. And then valproate molecules will be transformed using the Cytochrome 2C9. So first, we'll describe a biorecognition reaction that will happen in the antibody chamber or sample chambers. So after addition of the plasma sample, the valproate molecules will be captured by selective antibodies immobilized on microbeads. And then there is a washing step. So unbound molecules will be washed away using the phosphate buffer. And then there is addition of valproate molecules from the store chamber. And there will be an interaction between valproate molecules from the store chamber and the remaining antigen binding sites. And finally, unbound molecules in the store will be pushed out using the same buffer to the cytochrome chamber. And now my colleague Daniel will explain the working principle of the cytochrome chamber.
So moving on to the cytochrome reaction chamber, where we have 2 main elements. First of all, the gold electrode, and second of all, CYP2C9, which is a P450 enzyme in the human body, which will metabolize valproate among other many drugs. This enzyme will produce fluorine valproate, which is key to the hepatotoxicity that has inspired the SensUs competition this year. And the way it works is we wash the valproate from the previous antibody chamber, which will then bind the enzyme, consuming 2 electrons in the process. Now, to look a little closer at how this enzyme is immobilized, we need to look at a self-assembled monolayer, which will covalently bind the tail of the enzyme. And this binding is occurred in such a way that the conformation or shape of the enzyme is not altered, and the orientation of the enzyme opens up an iron group to receive the electrons freely from the electrode. And now, to understand how this works, we have to look at the catalytic cycle on the left, which will be very scary to engineers, and the cyclic voltammetry graph on the right, which will be very scary to the biologists. But fear not, it's actually quite simple. We just need to look at steps 2 and 4 with the red and blue arrows, and how they translate to cyclic voltammetry with the red and blue arrows on the right. So the way this works, we receive an electron in step 2, and it's shown again on the cyclic voltammetry graph to be a small current, as this is not a very favorable reaction and is not very likely to occur on its own. However, step 4, when we are in the presence of oxygen, the enzyme opens up upon binding oxygen and receives electrons more freely. Now, shown with the golden arrow is the key to this biosensor. The addition of substrate, in this case warfarin, is shown by Yang et al. In 2009, but in our biosensor will be valproate. This will open up the enzyme and stabilize it further so that more electrons can transfer, as shown by an increase in current. Now, what this results in is a substrate-dependent peak, which means that if you plot the current versus concentration of substrate, you will get a very clear curve, which will allow to determine the kinetic conditions of the enzyme and predict the specific concentration at which a current will occur. If we measure this current, we can therefore measure the concentration. Thank you for listening.
Thanks a lot. Nice pitch. And again, I would say the pitch is open for discussion. Tony, please.
Thank you. So that's very nice, very elegant solution to measure effectively the unbound sites on the antibody by titrating them with valproate and then measuring the unbound, non-captured valproate. Question I had is related to that, which is if you get any loss of antibody activity, any loss of binding ability by the antibody, that will give you an apparently higher amount of valproate in the sample. And I just wondered if you had any sort of controls built in to be sure that the antibody was actually capturing the full amount of valproate necessary?
Okay, so do you want to take this, Amin?
Yeah, go ahead,
Okay.
Daniel. That's okay.
Yeah, so actually we thought about this for the cytochrome chamber because it's also enzymes. So specifically we're thinking about the effect of temperature on this biosensor, and effectively the solution we came up with is that if you have the standard curve as shown in the pitch at the end, if you prepare the standard curve in different conditions, so if you anticipate temperature specifically is going to be very relevant to this, and you prepare this curve in the different temperatures, if you know the conditions at which the biosensor will be used, then we can adapt to the different result, just to plug it into the biosensor and get a different result depending on what you're expecting.
And as a second thought, for antibodies, we have included two different controls. The first one is the evaluation or determination of the active number of active antibodies, and also there is a second control to determine their orientation. So these two controls are necessary before the validation of the biosensor.
Okay, thank you.
Luz, please, yeah.
Yes, thanks for this presentation. So I was also a little bit worrying over. Well, I have some questions about the antibodies. So now, if you look at in your movie, you see that they're perfectly aligned and they have an equal spacing between each other, and that everything will attach to it. How do you guarantee that the layer of antibodies on the surface is always the same, or is the optimal? It has the optimal density to capture all these. All your biomarkers of interest?
Yeah, so first of all, we're going to use the protein G as immobilization support. Mm-hmm. So this protein G will enable the capture of antibodies from their FC region. So all antibodies will have the orientation end on. And also there is a control to be performed, which is the number of immobilized antibodies per bead. So we need to measure the number of using commercially available kits to make sure we have the right number on each bead, microbead. So
because that in the end will influence how much of the ones you add in the end that you are going to measure, how good it is. Because if you have a too low density, everything will be saturated by just what is present in serum. But if it's not that much, or if there are more binding sites, it might be that in the end it is more difficult to measure. So yeah, it's of interest. Yeah. Well, I'm looking forward to all these studies you are still going to do. Hopefully, in 7 years.
Actually, we are using a site-directed immobilization, not the traditional random immobilization, to make sure we have the right number and the right orientation. Main importantly, yeah.
Yeah. Okay. Thanks.
Okay. Anyone else? No. Of course, other people in the audience here are also free to ask questions if they want to. Then there's other teams present or so. If not, I can also actually express or I can come up with something. But my interest is of course also a lot the microfluidics part, being from a microfluidics company. But so I was intrigued by your gates or your flow gates. So it's quite nice. Maybe someone can go in a little bit more detail how that could work and give you sufficient control over basically the steps that you want to perform. It's a bit of an open question, but it would be nice if someone can shed a bit of light on it. It's kind of conceptual thing still in the report.
Sorry, I was muted there. I think with that question, unfortunately, our engineers are currently not in the call because Amin and I are both biologists. So unfortunately, I can't answer that question. Sorry. I believe they're flow actuated gates.
Okay, that's a pity. Also because my biology knowledge is quite limited, so I cannot really come up with smart biology questions. So I'm looking at other people in the call for that.
Okay, apologies for that.
That's fine, of course. So I think then more generally, I think that holds for a lot of the solutions actually. If you so you do some steps you need to get to your final signal. So there is, in a sense, a sort of sample preparation. Do you think that's enough? That will give you indeed the specificity you need?
Yeah. So the specificity, the antibody chamber. Amin can follow up on this if he wants. That does have the specificity we require. As for the enzyme chamber, the design I sort of showed by Yang et al. In the paper doesn't have the same specificity. It measures 1 micromole of substrate, and we need to measure as little as 1 nanomole. However, there is ways to increase specificity if after testing and validation of the electrode we can't reach the specificity. We can alter the immobilization of the enzyme with sort of a PAMAM and over-oxidized polypyryl structures and all sorts of things like this to increase the specificity of the electrode as required.
Okay. Luz, do you have a separate question you'd like to add to this?
Yes, I have a question about these magnetic beads that I use. So some of my students are also working with beads here in the lab, and I know that they are getting frustrated by the fact that they always cluster together. How are you going to avoid that?
Sorry, can you say that?
So these beads, you need separate beads to connect or to catch your biomarker. But what my students always notice is that these beads like to glock together, so that in the end you will not have a single individual beads, but you will have a cluster of beads. How are you going to avoid that?
Usually this can be like sorted out by keeping the chamber under agitation, but in this case we don't need to separate them because the remaining stored valproate will be flushed out to the chamber, cytochrome chamber. So like all beads with antibodies and captured valproate molecule will be like kept in the antibodies chambers, whereas the remaining antibodies, like unbound stored valproate, will be flushed out to the cytochrome chambers, where it will be like transformed by the cytochrome.
That's true, but if you have a clump of beads, so not individual beads, but a clump of beads, your density of capture molecule is less, and then the results will be affected. So so if I hear your answer, I don't think you expect that there will be any aggregation of these of the beads, but I'm wondering just if you consider this, or if you want to put it on the shelf, like for instance, someone has to take the test and then has to do it after 3 months that it was lying on the shelf. Are you still sure that it will give the same result?
Yeah, no, this is a really good question. I think there are solutions to this. You could perhaps immobilize the beads in some way because we can control how many antibodies are there. Maybe there's something like Apta's immobilization that you can capture the microbeads. You'd have to play around with the size of the chamber itself and the number of microbeads, but I believe it's something that with testing and validation you can go over.
Okay, thanks.
Thank you.
Thank you.
Perfect. Almost through in terms of time, so I think we won't take more questions now, but just wait 1 minute until the next pitch will be shown.
Thank you very much, guys.
As you can see in the figure 1, the main idea is a T-shaped microfluidic channel with two very differentiated inlets. One of the inlets receives a constant flow of air, and the other, the plasma sample, mixes with a surfactant called cetylpyridinium chloride, CPC. The constant flow of air creates bubbles that travel through the channel to a photodetector at the final. The bubble size depends on the surface tension of the solution. For that is used CPC because it's the surfactant that has the highest resolution. So the structure of the BPA molecule acts like a surfactant, therefore can change the surface of the solution where it's contained, including the blood. However, at therapeutic concentrations, this change in the surface is not measurable. Hence, CPC becomes necessary. Where the two flows converge, the bubble is generated and moves when it reaches the critical size. This critical size depends on the surface tension of the solution. Lower surface tension means the bubble reaches critical size faster. So bubble frequency increases when decreasing surface tension. Therefore, we can say the higher BPA concentration, the lower surface tension, and the major quantity of bubbles. Due to circumstances of COVID-19, our universities have been closed the recent months, and therefore we are not able to conclude the project, and we don't have a final image of the device. Basically, the prototype of the cartridge is made in PDMS on glass, and the reader consists of 3 parts: the hardware, the software, and a mechanical package. So the hardware is based on a PCB with an optical sensor that measures the amount of light, of incident light, depending on the bubbles created over a certain time. This PCB is connecting to a microcontroller embryo from an eye. The embryo, together with the PCB, are connected to a computer which will receive and process all the information, all the data. And at least the mechanical package has been designed to cover all the hardware from light and as a sample holder. As I said before, the project was interrupted by COVID-19, and we don't have any kind of results, but preliminary results were obtained to measure the correlation between bulk rate concentration and the surface tension done by OCA 50AC sessile drop technique using different concentrations of bulk rate saline solution. The graph basically shows the angles formed by the sessile drops. The angle of the sessile drop decreases with time, and its surface tension is low compared to water.
Thanks a lot. Very original approach, I have to say. Which has, of course, the advantage, the disadvantage that it's also challenging to prove when it's so new. But Philippe, would you like to comment on this?
Yes, thank you. So yes, I like the originality of the solution. Of course, it is as Marco mentioned, it's probably going to be challenging in real conditions. But when you show the preliminary results or proof of concept in your graph, it's not that clear what do you change in terms of vaporate VPA concentration, because you have in the graphs you have different numbers or different titles, IFT 1, 2, 3. What does it mean? Oh, no
we cannot hear. Maybe someone is answering, but you cannot hear you. So
okay, we cannot hear. Yeah.
No.
Okay.
So if anyone is answering, please check your microphone. And if no one is answering, then it would be nice to hear if any one of the Barcelona team is in the call at least.
Yeah. Maybe they have a microphone problem.
Okay, so you can also try the chat.
Okay.
Is anyone from the Barcelona team in this call?
Yeah. Can you hear me?
Yes.
Yeah.
So I think one of our teammates is having troubles trying to get to the call, but I can answer the question.
Yes.
So the different variables are the concentration of BPA, and they stand for 0.1, 0.5, 0.3.
Okay. Okay.
And the first one is 0 millimoles, if I'm not wrong.
Yeah. Okay. Now I get it. So please next time you make a graph, just use the numbers, because we have no indication on what it means, and even in the report it's not visible. Another question related to that, and you have already heard about the question of specificity. There are many parameters that can, probably other molecules that can change the surface tension in a complex matrix like a blood or plasma. Did you anticipate problems with that interference?
I think you're muted again. The previous Barcelona team member who answered.
Yeah, we lost him again.
Yeah, I think so.
Okay, I'm okay with the questions. I think it's.
Sorry. We did anticipate these changes, and indeed, cholesterol or other molecules such as fat acids can indeed change the surface tension. So we have measured that.
Okay. But I think the good thing is that you really went for a very, very original method, and that I like. But of course, it's also a very, very risky method in terms of unknowns and things to develop. But good job. Yeah, thank you.
So I had a question about materials. PDMS is notorious for adsorbing proteins, surfactants, and small molecules. And I wondered, it's great for prototyping, but maybe you need to think of alternative materials for actually testing out. And I wondered if you had any ideas or any thoughts about what you could replace PDMS by.
Hi. Did you listen to me?
Yes.
Yeah.
Yes. Okay. At first, we try PDMS because it's a material that we know and we have in the university for doing our microfluidic channel. But we don't have any kind of results, and we don't try the device. We don't have a construction, and we don't try with a real serum, human serum. We don't know, so we don't look for a different material for construct our device. But probably if we have been doing our tests, we have a looking for another solution for doing our channels.
Okay, thank you.
Luz, please, yeah.
Yeah, I also like the original idea of your your sensor, and I'm wondering. So now you are looking at the size of the droplets formed, or the bubbles formed. It's not droplets, bubbles formed. And then you will say something about the concentration. Will it help you if you measure the droplet of the bubble size over time? So I can imagine, for instance, that a part of that the bubbles will, if you put them a longer time in the liquid, that the volumes will change because of the properties of the medium. Do you think that can help you, or it will absolutely not help you?
Can you repeat, please? I don't understand. What do you mean with?
So you have bubbles, so you measure the size of your bubbles, isn't it? But the size.
No. The size, no. We look at the frequency
of
the
frequency. Yes. Okay.
Yeah. Because we have the T channel and the airflow, it's continuous, so a major concentration, less frequency, and we can know the difference, but not size, just the frequency.
You are not looking at size. So I was wondering, the bubbles size will change over time. I'm pretty sure. Maybe that will tell you something about the medium. You have can give you some additional information. I don't know if it will help you, but indeed, in your case, it will not help. Okay, thanks.
Mm-hmm. You're welcome.
I also have a question, actually. So you're adding this surfactant CPC, and this seems to work as a kind of amplification mechanism. Can you explain that?
Yeah, it's a surfactant because we know that BPA is surfactant, but in the concentrations we are working, it's not enough. So we add a surfactant, like it's similar, like we increase the concentrations of BPA, but it's just because the surface tension change, and we know the concentration of BPA. Knowing obviously the concentrations of CPC we add to the sample. It's just for increase the surface tension change.
But then you're changing your baseline, you could say, because the effect, the valproate effect on the surface tension will still be small, or unless there's kind of an interaction with the CPC, maybe to amplify this effect or not.
Yeah. CPC is going to amplify the BPA tension surface change.
Okay, and
it's just for enhance the BPA change.
Mm-hmm. Okay.
And also we know that the correct concentration to CPC for change the valve rate, it's 1 micromolar.
Okay. Did you also try any other surfactants yet? I know there was not so much experimental time available this year.
No.
Okay. Understandable again.
Thank you.
Okay, we have 2 minutes. Anyone up for a last small question? Apparently it was all very, very clear then. Yeah, well, I think then I can come up with some. Yes.
Hi, my name is Jorrit. I'm from the organization. Thank you for the jury for during this meeting, and I kindly ask you to move into the next rooms for the second round. At 2 sharp, we start with the next videos, and you should have moved to the next room then. So we have a transition time now.
Okay, perfect.
Okay.
Thanks to all the teams here, and great work. And hopefully we'll see each other again.
So, hello. Is it time for the next round?
Hello. Yes. I think in 2 minutes we are going to start with the next round. So.
Okay. So I'm the chair, I believe, for this session.
Yeah. I think we are waiting on the other jury members.
Okay.
And the team captains.
So I can maybe start with a short introduction for myself, because I'm not Annemarie. So I have no idea who the other jurors are. I think, Ernst, you're a juror? No.
Hi, I'm a juror, Michael.
Hi, Michael.
I'm here also, Maria.
And so we have Michael as a juror, and who's a juror as well?
I'm a juror, Maria.
Maria, okay.
Yeah.
That's it, I think. I'm sorry, I'm substituting for a colleague of mine. My name is Angela. I'm a clinical chemist in Utrecht, the Netherlands. And I apologize in front of, because I didn't have the time to read all the reports. So hopefully I won't ask too many stupid questions. Hopefully you can start with asking questions and I won't have to. And also I invite all the other team members to ask any kind of questions, just to, you know, to make it interactive event. So I think for now this sums up the introduction. I think we can start with the first pitch, the 4-minute pitch, which is by Minerva from the Imperial College London in England.
Hi all, we're Minerva, the team from Imperial College London, England. We're really excited to be presenting to you all our microcantilever biosensor, which will be used in the detection of free valproate. A company called Avacta have engineered protein scaffolds to be used in an alternative to antibodies called aptamers, which have none of the limitations commonly associated with antibodies. Avacta make custom aptamers using an online service and offer a strategic licensing agreement to customers who would like to use their aptamer technology in their products. Aptamers can be chained together and can also be immobilized on surfaces such as beads or plates. In the case of our sensor, we will immobilize the aptamers on the SU8 cantilever surface. The scaffold protein used in aptamers is adherin, which can be shown in these images. The images have been coloured depending on the secondary structure of the protein. So the helixes are shown in red and the loops in green and the chains in yellow. The two green loops at the top of the protein structure are the variable region. And by changing the amino acid in this sequence, the protein is not destabilized nor the overall structure changed. After making small changes, a series of proteins will be produced that can be screened against the specific molecule. In our case, it will be valproate, to determine the best fit. As aptamers can be more specific than antibodies, the non-specific binding in our sensor will therefore be very minimal, providing accurate results, as well as minimizing issues around shelf life and stability of the reagents.
The microcantilever base is made up of 500 micrometer thick silicon wafer. Due to wet etching, there is a top and bottom layer of low-stress nitride layer to protect the piezo-resistant component and act as a blocking mask. Following is a 4 micrometer polymeric layer of SU8. We chose this less commercially used material as it makes creating disposable strips more affordable. It also has a low elastic modulus, resulting in a greater deflection. The piezo-resistive layer is made up of 120 nanometer thick polysilicon. A layer of gold and chromium nanoparticles is to allow an electrical connection of wire bonding. To prevent the electrical components interacting with the ionic solution, a 600 nanometer thick nitride film is laid above. The final part is a smaller layer of gold and chromium where the SAM, made up of 8-mercaptooctanoic acid, and the Avacta technology is deposited on. To process the generated signal, we'll be using a Wheatstone's bridge and an amplifier into the microcontrollers to calculate the concentration. Our cartridge contains a custom microfluidic chip designed to move 10 sets of 3 droplets individually to the microcantilever using 4 syringe pumps. A drop of wash is pumped through the channels to wash any leakage and calibrates for a 0 concentration reading. The first drop does this with a known concentration of VPA to calibrate the microcantilever for the reading. The second drop is the patient's actual blood sample to be compared with the reference. The third drop is the wash to clean the cantilever for the next set. Whilst each drop at the cantilever, FVPA molecules diffuse to the aphamer surface and give a reading. During the short time needed for the molecules to diffuse from within the drop to the lever, the bound VPA molecules will not dissociate from their binding molecules in a significant amount. This slide shows how the overall device would look.
So we have used React Native software, which has allowed us to use one set of code to create an app suitable for both Android and iOS devices. This means that no one should be left without the ability to use our app. The screenshots on this slide show what the main features of the app will look like on an iOS operating system and the navigation alike.
Finally, the use of a microcamera also allows the device to be easily upgraded and maintained, and with developed Aphamer technology, the sensor can be adapted for sensing for a variety of drugs in the blood, making this one of the few biosensors that can be used by many different kinds of patients.
Thank you very much for this very interesting talk. Are there any questions from the public listening for Minerva? Nothing? So everything is very clear, I think. I see that you use the aphemers made by Avacta. This is already an established company that already produces these aphemers. Do you know what the specificity of these aphemers is for binding your specific product, so the VPA in this case?
No, we don't know an exact value to be able to tell you, unfortunately, because this would be a new aphamer to be developed. And also at the moment, Avacta are very preoccupied, as I'm sure you can imagine, with the current circumstances. So we haven't been able to come into a joint venture with them just yet, but it would be very hopeful that within the early stages of development that would be the case. We would like to use the technology in our products, but we can say that for other aphemers that have been developed, the specificity is very high usually, and you can tune it very well to your desirable compound, really. So we are confident that it would be able to be tuned to what we would need.
Okay, thank you. And what I didn't get is whether you were able to or are able to measure the unbound fraction. So you have a VPA that's bound to albumin mostly, yeah. And how do you correct for that?
So yes, at the moment it would be specific to unbound. However, we would be looking at doing a sort of adding a pre-reagent to unbind the valproate from bound albumin or whatever else it would be bound to in the blood. So we would probably look at maybe adding some acid, probably around pH 2, or some sort of reagent to dissociate the two.
That's if we want to measure all of it, as in if we just want to keep it unbound, as I think you said. The step that involves the interaction between the sample and the cantilever wouldn't involve dissociation of the bound. So it would just be measuring the unbound. It would be a very quick interaction, and so all the bound would stay bound to the albumin, and you'd just be measuring, ideally, specifically the unbound.
Okay.
Oh, I just lost everyone.
I'm sorry, I was muted as well. You can use the little hand in your screen to raise your hand, and you can ask a question. Yeah, that's it. Thank you, Michael.
Sorry, yeah, I wasn't sure if you meant public, not the jurors. So I had a question more on the hardware side. So I know you went with the cantilever type structure. Can you explain a little bit more about that type of hardware you plan on using and what type of back-end hardware you would use to interrogate the transducer? Are you looking at miniaturizing a network analyzer? Are you measuring a frequency response? How would you go about that?
So we'll be measuring the change of resistance, and we're going to be correlating that with the surface stress and the change of surface stress due to the concentration of VPA. And at the minute, we're going to be looking at that using a simplified Wheatstone bridge circuit, and we're planning to use an Arduino to program that.
Do you have any feel for the magnitude of changes you would see in terms of resistance?
Unfortunately, we haven't had time to do that because our labs have been closed. But I think some of the electrical engineers in our team have been working on that, and we have an estimate of what range we are trying to work for. So
sounds good. Thank you.
Thank you, Maria. You have a question as well?
Yes, I thank you for your report. I enjoyed it a lot. I thought it was an interesting idea to use cantilevers. I have a question. So you described that you have a droplet where you do calibration, then a droplet where you do measurements, and then you have a droplet where you clean. So my question is this because this is supposed to be like you have a cantilever and this is permanently there, or is it going to be switched from measurement to measurement? Why do you need to clean?
So the clean is because the accuracy of our device relies on doing with one disposable chip, you do around maybe 10 measurements. So it's not permanently there. Before like the one use, you have the sample and that gets separated into 10 drops. And so between each drop, you need to clean the lever so that no valprate stays on there.
Do you have any idea how plausible that is? I mean, usually cleaning, binding between molecules and your sensor is not very easy, and you cannot be certain that it happens.
That is true. If we had more lab time, we would start off by making a very simple prototype of this chip, and we'd actually test it out. It may result that it may be possible that there's actually a predictable, like, what would you call it? As in, like, maybe some valprate stays on the cantilever, but it's a very predictable amount. And so you can actually account for that, maybe. Maybe you have to leave the solution there for long enough for the valprate to dissociate from the lever. So that is, yeah, we don't know how plausible it is. It is in principle plausible, but yeah, we'd have to prototype it very extensively.
Yeah. Thank you.
So we have 1 minute left. Van IJzendoorn, I don't know your first name. You had a question as well?
Yeah, in fact, I had a similar question about the cantilever. That's why I lowered my hand again. But maybe I can.
Sorry,
but it's okay.
Maybe another question.
Yeah, I can also ask another question. It's still not completely clear to me how the detection occurs, because in your report, I think you speak about surface stress. And basically, there are two ways usually these cantilevers are read out, indeed by their resonance frequency, but the other is actually by their deflection. And usually there's a direct relation between the mass and the resonance frequency. So that's one way to measure it. And the other is actually to measure the deflection straight from a light beam by a displacement due to the surface stress. And I was a bit puzzled about your explanation that you were using a Wheatstone bridge to read out, but it was still not clear to me whether it was a frequency or a shift, or how do you actually do that?
So we try to establish a relationship between the change of resistance in our circuit and correlate that to the change of surface stress as well as the deflection. We tried to do that using a...
Which resistance are you measuring?
So due to the deflection of the beam, there is a change of resistance on the micro cantilever. and we're trying to we've found an equation.
So you use basically a detector which induces a change in resistance.
On one side of the cantilever, there's a piezo resistor, and so as it deflects, that will cause a strain in the piezo resistor, and that will change its resistance. Maybe I wasn't clear enough. Yeah, there's a resistive element, and that connects through two terminals to a Wheatstone bridge. And so as that deflects, the deflection, it wasn't directly being measured. We might have to measure that in a lab to develop the device. But yeah, it's a resistor on top.
Okay. So
okay.
Now I get it.
Thank you. Thank you. I have to stop this pitch. Thank you very much for the nice presentation, and good luck to you, guys. So then we can go to the second pitch, which is from Upsense, Uppsala University, Sweden.
Welcome back to Upsense, the Uppsala University Census team. In this 4-minute pitch, we'll be going through all the major facets of our biosensor. We'll be explaining the sample transport, molecular recognition, physical transduction, and data processing, as well as showcasing the feasibility of our biosensing device with our scientific results. To start off the analysis, the plasma sample is injected into a microfluidic chip, which by laminar flow diffusion separates the BPA from the plasma phase into a secondary buffer phase, which effectively cleans the sample from larger molecules. Using COMSOL multiphysics modeling software, we have been able to optimize the flow rate such that we maximize BPA diffusion while minimizing the diffusion of blood protein and reagents. Thereafter, a mixing step occurs to let BPA interact with our reagent. Here, reagent refers to coated gold nanoparticles. The coating consists of a molecularly imprinted polymer, or MIP for short, which is responsible for the molecular recognition. We have synthesized a custom polymer around 50 nanometers colloidal gold particles to selectively bind BPA. Our very own quantum chemical DFT calculations at PBE, Purdue, Berkeley, and Saarhof level of theory have shown binding between BPA and the functional monomer of the polymer. It ensures that BPA is selectively brought close to the gold nanoparticle, an integral part of the physical transduction, which happens by surface-enhanced Raman spectroscopy. Raman spectroscopy is a well-established spectroscopic method which measures vibrational properties of molecules. Historically, it has been limited by a lack of sensitivity, but advances in instrumentation and methodology have increased its applicability. One such methodology, SERS, surface-enhanced Raman spectroscopy, is a distance-dependent phenomenon which increases Raman spectroscopy signal intensity at colloidal metal surfaces. Utilizing a green laser and an optical detector, we can perform Raman spectroscopic measurements which selectively boost the BPA signal without increasing background signals. The data is processed via peak picking and integrating the peak area against the calibration curve. The spectrum, as well as integrated result, are shared in cloud server and can also be observed on our user-friendly touchscreen display, as can be seen here. Our biosensor has the potential to measure BPA over the entire therapeutic range. Literature states that SERS is capable of detecting up to single molecule concentrations. The main challenge faced by our team was the development of a coating protocol for our novel imprinted polymer, which we succeeded at, as evident by our experimental results, which show the release of BPA and a corresponding signal decrease from our coated particles. Furthermore, our sensing setup, which is depicted here, has the possibility to expand its biosensing capabilities simply by altering the molecular recognition polymer. A different composition can have the ability to observe various analytes separately or simultaneously, as long as they are separated on the Raman spectrum. It should be mentioned that although our biosensing system has been developed for plasma analysis, it could be used directly on blood samples as well, since our initial separation step already separates BPA from larger molecules, proteins, and cells. We want to take this opportunity to thank our generous sponsors for their support along our year-long journey, and you, the audience, for your attention. Thank you very much.
Thank you for this nice presentation. A very interesting, innovative technique to use in a model. Are there any questions from the audience for UpSens? Anyone? Okay. Oh, yes, Michael.
Thank you. Great job, guys and girls. So I think I have two quick questions, maybe. One on the separation technology. So typically in microfluidics, when you have laminar flow, you don't have a lot of diffusion across that barrier. Can you estimate the amount of time it would take to separate the necessary amount of VPA to diffuse across that barrier to make a measurement? So that's my first question.
Yes, I can answer that. So we've built models in console software to simulate this process, and from there we can show how much distance and how much pressure is needed to get sufficient diffusion to keep diffuse VPA and also keep the proteins out. So we've optimized this distance and pressure using these simulations. So you can actually show this.
Do you have an idea of the time? I didn't remember seeing the time. So does it take 5 minutes to stabilize? Does it take 10 seconds to stabilize and get enough sample for measurement?
No, it's very little time that is actually in the separation channel. I think it's actually less than 1 minute.
7.5 minutes with the pump speed we use.
Okay, so it's half a minute in the actual channel for diffusion.
Gotcha. And the second question I had regarding the SIRS measurement is typically SIRS and other Raman are done by fingerprinting the molecule versus the background or versus other targets. Do you have to increase, or have you looked at the computational power that you would need to do fingerprinting of the VPA? Would you need to do that, or is it a single peak that you have to identify to say this is VPA and this is quantitative?
I apologize. The idea is that since we have the selectivity step with the molecular imprinted polymer, that only the signal of our analyte actually gets enhanced, which is why we don't have to do an extensive fingerprinting, since we know what peak we expect and only the peak of our analyte actually gets enhanced. So gotcha. We know what peak we're looking for.
Thank you.
Thank you, Michael. Yes, first, Mr. Eisendorn.
It's Leo, by the way.
Leo.
I would like to ask a question also about the SIRS technique. SIRS is known to be very sensitive to the distance of the molecule to the surface. You plan to have a small MIPS kind of layer around the particles that actually recognizes and binds the VPA. And I was wondering, how good can you control the thickness of that film, and how thick is it actually? Is it within the range that is reasonable for SIRS detection?
So yes, SIRS is very sensitive to the distance, which is why we decided to go with a polymer film, which theoretically is not limited by how thin we can make it if we manage to control our production parameters well enough. Sadly, we have not yet been able to confirm how thick exactly the film is we produce with our current setup. We've only shown that we can make the polymer hull around it, but theoretically, through controls of temperature, time, and reagent concentrations, we should be able to very accurately limit the thickness of the coating, which should stay in the range of a few nanometers.
Okay, fair enough.
Yeah, that would be subject for further investigation.
I think it will be difficult, but
yeah,
something to optimize is good.
Thank you. Maria, you had a question as well?
Yes. I will go a bit to the device that you mentioned, your reader device. So you mentioned that it's a 5 kilogram instrument. and that it also has a huge power consumption also when it is idle. And I was thinking about, this applicability in terms of point of care. So that is one of my questions regarding the reader. And then the other one also related to the same is that you also mentioned that you have to type in a lot of parameters before actually operating the device. So I was sort of thinking about the user friendliness part. Have you thought a bit about that?
So first of all, the device will be a hospital device for primary care units. So it is not the wearable device, but the portable. It should be plugged in. But in the report, there is indeed some error. So the idle power is less. It is around 4 watts. While during operation, it can go up until 15. I know that was an error in the report. And thus it should be okay. And then in terms of the parameters, those are only initially to be entered while the device is being manufactured at our company. So once the end user would get the device, it is already all everything would be already parameterized and everything would already be okay. So the end user doesn't have to do it.
Okay, that's fair enough. Thank you.
Okay, thank you. We still have 3 minutes left. Is there somebody from other teams that are interested in asking a question? No. Yeah, so maybe it's my omission, but I was wondering whether there is interference because of excess gold particles, because the nanoparticles you need to so it's bound to the polymer, and then you bind the VPA, right? So do you need to like wash, have a washing step, or is it not necessary?
What do you mean exactly by excess gold particles, like non-coated gold particles?
Non-bound, non-VPA bound, because you want to measure your VPA, so you have like a peak at the where you think you need it, where it's supposed to be. But do you have like interference of the other unbound particles?
Ideally, the only signal we would see is the pollen signal of the polymer and the Raman signal of the VPA, since that's what should be selectively bound. And we kind of know what to expect in terms of the polymer signal, since with a constant concentration of gold nanoparticles, that one should also be relatively constant if we get the coating protocol optimized enough to produce consistent results.
Okay, do you need like a reference as well, or a calibration, something like that?
Yes, for the quantification, we would need of the VPA, we would need an internal reference standard. We still have to decide whether that would be an extra compound which is mixed in with the gold nanoparticle serum, or if we can use the polymer in the coating as the reference. But that would depend on how consistent and how accurate our coating protocol actually is, which would be something we still have to test in the lab.
Okay. Okay, I understand you didn't have a lot of time to test it in the laboratory, right? Because of the COVID.
Yes, we had some restrictions. We were able to show that we can coat the gold nanoparticles with our polymer, which was like a big proof of concept for us, but we didn't have much time to test all the details of the coating.
Okay, thank you. Maybe one quick question, 1 minute. How's the weather? No, I'm just kidding. Maria, you have a quick question?
Just a very, very quick question. So if I go back to your simulations and the diffusion, already there you're sort of making your life a bit difficult because you're halvening the concentration that you can measure. Because at the best of the case, you can only get half the concentration out. So that's maybe something you should consider a bit if you have to go to the low concentrations. And then you mentioned that it will work with full blood also, because you're also, so I mean, full blood is a non-Newtonian fluid, so there you have already some issues with have you tested a bit if you can do that actually? Or have you read something in the literature? Can you get, the buffer and the full blood to flow together in a sort of diffusion sorting system?
No, we haven't done any testing with full blood. The premise of that statement was basically that since we do size separation on the first part, you should get any large molecules like proteins or even whole cells out before we go to the analytical part of the sensor. So in that sense, full blood wouldn't make a huge difference compared to plasma for us, since we already have that first step where you basically have the same as centrifugation. And then, of course, also because of the MIP, it's a very selective biosensor, because all of the molecules will basically be like destructive interference, so they will not build up, unlike VPA. And for the halvening of the concentration, this is definitely true, and this is also something we discussed, but because SIRS can be so sensitive, we feel like these two techniques work well with each other. So on one side, it's a downside because we halve the concentration. On the other side, the SIRS is so sensitive that this shouldn't make a huge issue.
Thank you.
Great. Well, thanks again to you, and very nice product that you designed, and good luck to you in the competition as well. Thank you.
Thank you.
Thank you very much.
Thank you very much.
Thank you.
So then we will go to the third and last team, which is Test from the Technical University in Eindhoven.
We propose a biosensor that uses novel techniques to measure the concentration of VPA in blood plasma. Our biosensor runs completely automatically and is therefore very convenient for both patients and medical professionals. Our biosensor is 13 by 13 by 8 centimeters small, which is why it is perfect for a point-of-care device. Our microfluidic cartridge has the shape of a disc, and through the spinning motion of this disc, the fluids on the cartridge will be transported through the channels. The first chamber that the blood flows to is the filtration chamber. Here, albumin is captured and isolated from the sample by magnetic separation. Magnetic particles that are functionalized with anti-albumin antibodies bind to all albumin molecules, including those that have VPA bound to them. When a magnetic field is applied, all albumin will be isolated to one side, and the rest of the fluid can flow through to the next chamber. In the next chamber, the assay reagents that are freeze-dried are now dissolved in the fluid. The assay consists of two major components. Firstly, the VPA analog that is bound to split enzyme small bit. And secondly, the anti-VPA antibody that is conjugated to split enzyme large bit. When small bit and large bit bind to one another, they form the complete enzyme nanobit, which is bioluminescent, meaning that it produces light. Nanobit can only be formed when small bit and large bit are in close proximity, and that happens when the VPA analog is bound to the antibody. Because the VPA from the sample is in competition with the VPA analog, the resulting signal will be inversely proportional to the VPA concentration. To correct for environmental factors such as pH and temperature that might affect the efficiency of the nanobit enzyme, we add a reference enzyme. This enzyme also is bioluminescent, meaning that it produces light, but this time in a different wavelength. Finally, the ratio between both signals will be calculated to determine the VPA concentration in the blood. Because light is produced in two different wavelengths, we will also use two diodes. With filters that separate the light by wavelength that are placed in front of the diodes, one diode will measure the assay signal, while the other diode measures the reference signal. With the use of an app, the patient operates the biosensor. With the app, they can also record and document their epileptic seizures and side effects, and also share all the data that is processed by the biosensor to their doctor. Our biosensor uses state-of-the-art technology to provide epilepsy patients with the correct blood concentration of free VPA and is easy to use. Complete sample handling from blood droplet to readout is completely taken care of inside this device, including an albumin filtration method.
test for a life worth living.
Wow, thank you. It looks very nice, a prototype already, and a lot of sponsors as well. So congratulations. We will now take questions from either the jury or the audience. Maybe I can start then with the first question. So you use a albumin filtration system, so that's very nice with the magnetic beads, but how do you ensure that there is enough time for the binding of the magnetic beads labeled antibodies to the albumin? Could you explain that?
We ensured that there was enough time by also placing a magnet at the bottom and at the top of the chamber, the filtration chamber, and switching the magnetic field, making sure that it can really combine. We also saw that within 30 seconds, most of the VPA would bind to the that the albumin would bind to the anti-albumin antibodies. So we are not completely sure, but we guess it would be within a minute of binding.
So, and there's enough, like a lag time that the fluid stays in that compartment? You have like a mechanism for that, or it just flows by?
We have a mechanism for that. I think Leandra can tell more about it.
Yes, in the cartridge, we build in fluidic stops. So the fluid can't pass completely by the filtration chamber unless the disc is spinning, which will be regulated by the device. So there will be a program that says, okay, after this 1 minute of filtration, we'll start spinning again. So the liquid will really stay in the filtration chamber.
Great, thank you. Maria?
Yes, thank you. Very nice work. I have two things actually. So you start by saying that you assume that your antibody would bind to both the VPA, the free VPA, and the one bound to albumin, right? Did I misunderstand that?
That's correct.
Yeah, the antibody, does it bind to the albumin or to the VPA in the first place? Is it? It's albumin, right?
Well, we use two different types of antibodies. In the first step, to filter out the albumin, we have anti-albumin antibodies. And after the filtration is done, we proceed to another chamber, and there we use anti-VPA antibodies.
Yes. So for the first step, where you have to bind both the albumin and the albumin with VPA, are you sure this can happen? So is there room enough on the albumin to bind to both things? I don't know, it's just a question. So
yeah, albumin is quite a large protein. Yeah, well, it's a whole protein, while VPA is only a very small molecule. And we think that if the antibody is really specific to albumin, then the small piece of VPA won't interfere with this antibody. Well, that's our assumption.
Okay.
Yeah, that it won't interfere.
Yeah. And then the second question I have is you've done very many calculations on the feasibility of the device. That was really nice when you couldn't test it actually. So you have this comment about the amount of the volume of nanoparticles, or magnetic particles. So you say something that you calculate you need 140 milliliters or something, and you have some microliters available on your chip. And I thought that sounded as a lot, the 140 milliliter. So can you comment a bit on that? So how are you going to solve this problem?
Yeah,
our conclusion indeed was that the volume needed for the filtration step was too big, too large, because of the 140 milliliters compared to the 200 microliters that we can access. Therefore, we didn't really look into it that much due to time reasons, but we suggest maybe combining this filtration step using the magnetic particles with another filtration step. This could be other filtration steps that are already commercially available, such as ultrafiltration, but not. Yeah.
I'm not sure if I'm right, but you know, some particles actually have a higher loading capacity than others in terms of how many antibodies they can have around the surface. So you could also look into that. Yeah. Thank you very much.
Thank you. Michael?
Thank you. Thanks, team. Great job. I had a question. You did a lot of simulations and predictions on the sensor sort of chemistry side. I was curious if you proceeded down that route for the optics or the photonic side of things. And what is your estimate of the amount of light you can actually generate for these very small concentrations, number one? And number two, you mentioned the dual LED system, which is fine. What type of detector systems would you use if these are very, very low concentration or low photonic yield systems?
Yeah, I already did some estimations on the amount of light that would be produced, because we already estimate how many enzymes there will be, and we think that there's 1 photon released per enzyme. So we actually converted that already to a power signal. Yeah, from the top of my head, I'm not sure what this magnitude would be, but we will use diodes, and we already chose them. And when you convert this power, when you absorb this power with this diode, we find that there will be around 40 microamperes of current that will be measured through the diode. So this 40 microampere will be detected by this diode, or produced actually.
Sounds good. So that's a lot. So that should be okay then. Thank you.
Yeah, we use pretty sensitive diodes for this.
And in relation to that question, why did you choose then just like a one-step assay? Well, you don't need amplification because of your diode probably, but you chose like a one-step assay instead of a two-step assay, where you can like magnify or amplify your reaction with a enzyme and substrate reaction, for instance. That would improve your detection yield, so that you either need less volume, because that's going to be a problem maybe, or you need less sensitive, cheaper stuff to read the results. So that, well, I don't know why you chose like a one step. That's the question.
That's a really good idea, because that would indeed improve the biosensor in terms of maybe needing less sensitive diodes or maybe making it cheaper. But we just started with some volumes that we had and looked whether this is feasible. And using this diode, it would still be possible with these volumes. But I agree, we could optimize this by maybe reducing all the assay reagents. So that would definitely be something that we could look further into when we go further. But we did not reach that point yet.
Yeah, and that's also, I'm sorry, am I interrupting somebody? No, I'm just gonna go on. And what I was also questioning was the coupling of the bits. The bit is directly bound to your antibody. And are you not afraid of a specific binding with the analog? Because you don't need specific binding of analog and antibody in order to complete your bit. Do you know what I mean?
Mm-hmm, yes.
Because you said it's, or I see in the presentation, it's in close proximity, but I don't think that it really needs coupling in order to get the full bit.
Yeah.
So can you comment on that, whether that would impact your specificity?
Mm-hmm. Yes, we also took into account that free floating
small bit could also bind to the large bit, although this amount would be much less because the binding of, well, the making of the complete bit is much more favored when it is bound to the antibody than the percentage that is created in the background, as I say it, will be very, very small. And also we can actually modify the binding specificity between the small bit and the large bit. And when you make the dissociation constant very high, so high dissociation, then already the probability of loose PPA analog and small bit or background signal creation will be a lot less, while there's still a high favorability when the bit is bound to the antibody. So there will still be some background signal created, but the fraction of this will be a lot lower because it's just that the concentration will be so low that the fraction does not really interfere with our assay.
Okay, and this probably also be dependent on your blood VPA concentration, whether you have less background. So if you have more VPA in your blood and the concentration is higher, then you get like a competition with your analog probably. So, that's of course for the next round of testing. I see the time is already 2 minutes past. So with this, thank you again, Test, for your nice presentation and nice product already. Almost finished, I think. And good luck with the competition. And thank you everybody for listening, and the jury, of course, as well. Thank you.
Thank you.
Thank you.